Bismillah ar-Rahman ar-Rahim. We started talking about the distant vector routing protocols, and we said that we have three examples in distant vector routing protocols. The routing protocol, the routing information protocol, which is RIP, interior gateway routing protocol, IGRP, or enhanced interior gateway routing protocol, EIGRP. And we said that vector routing protocols, the main feature is that the route is defined by both a distance and a direction. A distance to the final destination and a direction. And we gather this information, the distance and the direction, through periodic updates between the different routers. So the main characteristics of the distant vector routing protocols in general, the first thing is that they do periodic updates. So updates are periodic, even if there is conversions. The routing, the periodic updates will continue, even after conversions. Why? So once we reach the state of conversions, the periodic updates still going on. Why?
Maybe because there will be some new addition.
Yes, so if there is any topology changes, then we need to capture this topology change. That's why the routing updates have to be continuous. So the first thing is that periodic updates they facilitate the exchange of the routing table information from one router to another. Based on that, the routers will receive information, will update the routing table accordingly, and then in the next round, they pick all the information from the routing table and they exchange it in a broadcast fashion. When they exchange it in a broadcast fashion, it reaches to the neighbors. Okay. So route updates, the domain or the limit for the route update is the neighbors only. Okay. Unlike link state, as we said, the link state will be exchanged with the entire network. Right? So the link state will propagate through the entire network. But here the periodic updates will be exchanged with the neighboring routers only. So when we send a route update, the route update will go to the neighboring routers and then they will stop. The neighboring routers will pick this information, they will update their routing table based on the received information, and then in the next round, they again send route update. So it always works as one hub broadcast, unlike link state. Link state, the state of the link will go this way, and then the same link state will go this way, and it will propagate through the entire network. So so the routing updates, they work as broadcast updates to the neighbors only, and they happen periodic. The entire routing table will be included in the routing update. So every time the entire routing table will be picked up and will be inserted in the route update, and then it will be sent.
Yeah, you said they always send it to their neighbors?
Right.
And how is it broadcast?
Broadcast to the neighbors. It's like one hub broadcast. So for example, this router will send it to this router and this router. Okay? So this router will send it here and here. It's broadcast, right? This is broadcast. This router will then get this information. It will not broadcast it further. It will not broadcast the same information further. Instead, it will process this information, update its own routing table. In the next round, it picks up its own routing table and then it broadcasts. Okay? So that's why I said it's one hub broadcast. One hub broadcast. Okay. So of the distant vector routing protocols. So the routing protocol algorithm, as we said, it defines a procedure for accomplishing the routing task. So the send and receive updates. They facilitate the exchange of any topology changes, and then based on that we calculate the best path. So the routing algorithm calculates the best path, which, as we said, is very simple. The processing is very simple. If the incoming information is better than what I have, then I will update the incoming information in replacement to the information that I already have. It's very simple. Okay. And then it detects to react, or it detects the routing changes, and this is the trickiest part. This is what we are going to talk about today mainly. So detecting the changes is a very tricky job, and as we will see, it might lead to inconsistent information in the routing table of all the routes, and this will have some implications in terms of routing loops and so on. So the criteria based on which I evaluate a certain routing protocol, how can I say that this routing protocol is good and this routing protocol is not good, or this one outperforms a certain one? Okay, so this is a list of criteria based on which we can say that this routing protocol outperforms or performs better than another routing protocol. The first thing is the time to conversions. So if the two routing protocols they start together, which one will reach to the conversions faster? And as we said before, the conversions is a state of consistent information in all the routing tables of all the routes, such that any route update will not introduce any new information to the information which is already in the routing tables. So the first criterion is what we call a time to conversions. The second one is scalability. So when the network grows large, does that affect seriously the routing protocol or not? Affects it from the perspective of, like the time to conversions increases, the amount of memory consumption increases, the amount of CPU processing increases drastically. Okay? So scalability talks about the fact that when the network grows very large, does that affect the performance of the routing protocol significantly or not? Some routing protocols, they are very light in terms of processing, okay? And as we said, distant vector routing protocols, in general, they have incomplete view of the network, okay? And the route updates is localized. It's like one hub broadcast, okay? This actually nominates the distant vector routing protocols to be highly scalable. The only problem with scalability with respect to the distant vector routing protocols is the time to conversions. When the network grows large, the conversions becomes very slow. This is the main problem with scalability. Okay. Resource usage. Resource here, we mean by resource the memory. So the router has certain resources in terms of memory size, in terms of CPU processing power, and the bandwidth of the link, which is consumed by the route updates. So these are examples of resources that we care about here in terms of resource usage. So, so resource usage here refers to memory size, CPU power, CPU consumption, and bandwidth consumed for updates. Okay. So this is what we mean by resource. There is some other examples for resources, but يعني, these are the most important ones. So in terms of memory size, will the routing protocol consume reasonable amount of memory? Again, this criteria is for comparing two routing protocols. So, when I want to compare two routing protocols in terms of resource usage, I start the routing protocols. After some time, I check how much memory does this one consume compared to the other one. What is the amount of CPU consumption which this routing protocol consumed compared to the other one, and so on. How frequent the route updates are, okay, and so on. And then the implementation and maintenance. By implementation here we mean the simplicity of the implementation. How simple the implementation is. So for example, the RIP implementation is very simple. Why? Because it's based mainly on the number of hubs and the routing updates are periodic. So it's very simple. When you receive the route update, you just check the hub count in your routing table compared to the hub count in the incoming message. If the hub count in the incoming message is smaller, then you update your routing table accordingly. If the incoming message has a hub count which is more, then you just ignore it. Very simple procedure. So in terms of implementation, it's very simple. Okay. The criteria. So based on that, the distant vector routing protocols in general, they have the advantage of simple implementation. So based on the RIP version 1 and version 2 and IGRP, they use very simple implementation. You just check the incoming message to see if the metric in the incoming message is better than what you have. You update, otherwise you just ignore. Very simple. In comparison to that, the link state, as we have discussed briefly before, in the link state, you have a link state database which contains all the links in the entire network. To calculate the route update, you just have to parse the entire table and calculate if I want to go from one position to another, which links I should go through. So the calculation here is heavy. The implementation will be heavy because it's based on global view. Okay? So in terms of implementation, of course, distant vector routing protocols is much simpler. In terms of resource usage, it's also very simple. Why? Because it's based on the fact that you always maintain one table, which is the routing table, which you have to maintain anyway, right? And it contains the information about the destinations and the direction of the destination. So in terms of memory size, it's very reasonable. Whereas for the link state, you have to maintain a huge table of all the links in the entire network, and you also have to maintain the routes. You have to maintain you have to cache the routes in addition to the link state. So the memory size becomes larger. In terms of CPU power, again, distant vector routing protocols is very reasonable in terms of CPU power. Why? Because again, the amount of processing that you need is very light. It's very light. You just compare the message and update your table accordingly. Rather than in the link state, you just again have to process the entire link state table in order to calculate the end-to-end route. طيب. The disadvantage is also here, of course, the route update happens infrequently. So the amount of bandwidth taken by the route updates is also reasonable. Okay, but in terms of disadvantage, because of the periodic updates, the time to conversions tends to be large, especially when the network grows very large. Okay, which causes limited scalability. So this is these two disadvantages are based on each other. Because of the slow conversions when the network grows large, and that's mainly because of the route updates. The route updates happens, for example, in RIP every 30 seconds. So imagine if you have a very large network, and every 30 seconds you send one hub broadcast. Every 30 seconds. So you can imagine you can spend like minutes to reach to the state of conversions. And if there is any route topology changes, then in order for this topology change to propagate across the entire network, it also takes a few minutes. Okay? So based on that, of course, the scalability becomes an issue. Based on this, the slow time to conversions, scalability becomes an issue because scalability talks about the fact that when the network grows large, the performance will be affected drastically. So by increasing nodes and links to the network, the performance goes down. So that's not good. So these are the advantages and disadvantages. So based on that, the sequence of updating the routing table happens as follows. So when the router initially starts, as we said before, each router will discover the links that's directly attached to it. That happens by default. So when each router starts, this router will discover this link and will put it in the routing table. And of course, the directly connected links have a hub count of 0, which indicates that these are directly connected. And this discovery happens automatically because when these interfaces start, they directly discover the links directly attached to it, and they put it in the routing table. So this is the initial state. Okay. Based on that, once you start the routing protocol, this information needs to propagate through the entire network using the periodic route updates as we said before, until we reach to a state of convergence. So let's see how we can reach to a state of convergence in this simple example. Okay. So the initial exchange of routing information, this is the first round of exchange. So in the first round of exchange, this router will send information about the directly connected networks to router 1 and to router 3. Okay? Remember that these directly connected LANs, they share the link between this router and this router. And this directly connected link is shared between this router and this router. Okay? So based on that, this router will use only one row in the table, which is this link. Because this router does not know about this link. Right? And similarly, this router does not know about this link, so it will insert it in the routing table. Okay? So that's very easy. In return, this router does not know about this link and does not know about this link. So using one message update, I was able to insert one row here and one row here and two rows here. Why two rows here? Because this router 2 does not know about this link and does not know about this link. So this IP and this IP represents this one and this one. Okay, is that clear? So this is based on one message update exchange from each router to all the other routers. So when this router sends the message update, it gets broadcast and it reaches router 2, and so on for router 1 and router 2. So the routing update received from other routers, of course, when this router receives information about this link here, this router accepts it because it does not have an entry for this link, right? So it accepts it by default. Why? Because the default metric here is infinity. Since I do not have any entry for this link, I accept it regardless of the metric. Okay? So when I accept, this is very important. When I accept the entry, I have to increment the metric. Why? Because this indicates that if I want to reach to this network, I have to go through this router, which is one hop away. So when I receive the route update, remember that I have to increment the metric here. This has to be done. Okay? So the metric is updated and the new information is stored in the routing table. So I have to do both. Okay? And the question here, did I reach the state of convergence using the one message update exchange or not? Is this a state of convergence? Again, the state of convergence is defined as any further message update will not contain any new information for me based on the information that I already have. Okay? So based on that, we have performed one message update from each router to all the other routers. The question is this enough to reach to the state of convergence or not? Why? After I added this information. Okay? Is this a state of convergence based on which if I receive any message update from any router, it will not contain any new information to the one that I already have? In other words, does each router have enough entries to all the destinations in this network or not?
This is the only routers that we have, yes.
Right.
Because any further information will not affect the.
Okay, so this router, for example, has destination to this link, right? And this link, which are directly connected. And this link, this one. So this router does not have any information about this link yet. And this router does not have any information about this link yet. Right? So we need to do another message update, another round of route updates. So this router most probably has information to all the links. But only this router is missing this one, and this router is missing this one. So we need another round of message update. The router 2 will broadcast route update to both routers. So this router knows about 10.4.0.0, which is directly connected, but does not know 10.1.0.0, which is this one. So this router will insert 10.1.0.0 and will increment the metric. And this one will do the same for this network, which is 10.4.0.0 and will increment the metric. So now each router has entries for all the destinations in the entire network. So this is a state of conversions. Okay? So you can try to see any further route updates. They will contain no new information. So this is indeed a state of conversions. So routers continue to exchange routing information despite the fact that they have reached the state of conversions. Why? Because we need to account for any changes that might happen. And this is the trickiest part, which we need to talk about. A change that could happen is, for example, you have one link goes down. This LAN, one link goes down. Okay? One link gets added. One router goes down. Or one router gets added. So these are changes that we need to detect, okay, either directly or indirectly, and we'll see the difference. And we need to propagate this change to the entire network. And this is the trickiest part, because we will talk about some examples. If this is not done carefully and in the right way, this might lead to inconsistent routing table information, which will lead to serious implications. This will cause serious implications. Okay, we'll see that. So the conversions must be reached in a network before it's considered completely operable. Operable معناها يعني operational. Before that, there is inconsistency in the routing tables of all the routers, in which case that might lead to wrong routing, wrong forwarding for the packets, which might lead to some packets getting lost, or some packets go into a loop forever in the network. The speed of conversions consists of two independent categories, two things. The speed of broadcasting the route information, how frequent I exchange the route information, and the speed of calculating the routes. Calculating the route is based on the procedure or the algorithm that you use, which in the case of distant vector routing protocol, we said that the algorithm is very simple. You just compare, you perform certain simple comparison. Based on that, you decide whether you need to update your routing table or ignore the message update. Very simple. But when the network becomes large, this speed of conversions in the case of distant vector routing protocols, because of the periodic updates, it may take significant amount of time. So both REP version 1 and REP version 2, they use periodic updates. And the frequency of update here is by default around 30 seconds. So every 30 seconds you need to gather, you need to collect all the information in the routing table and broadcast it to all the neighboring routers. Okay? So this is what we call the route interval, or the time interval based on which we broadcast the message update to all the neighboring routers. So when this time comes, each router will get the information from the routing, all the information in the routing table, all the entries. We'll put it in one message, and then it will send it as one hub broadcast. Okay? EIGRP, okay? EIGRP uses different way of message updates. EIGRP has certain features when it comes to message updates. The first one is that these message updates are partial, are trigger based or event based, and they are bounded, and they are non-periodic. Actually, non-periodic should be first. So non-periodic means it's triggered, meaning that only if there is a change, I send it. I need to send message update. If there's no change, then I don't have to do message updates. Okay? Partial talks about the fact that I don't have to include all the routing table in the message. So I include only the change that happened. Okay? So pay attention to the definition of each of these concepts, because you need to be accurate in defining each one. Okay? So non-periodic means it's trigger based. So if there is a change, I send. If there's no change, then I don't send anything periodically. Partial talks about the fact that you send only the change that happened. So I don't have to collect all the information in the routing table and send it. Okay? Bounded talks about the fact that you report the change to the routers that will get affected by the change. Okay? So you don't by default use one hub broadcast. You report this change to the routers amongst the neighbors that get affected by this change. Okay? So this is the difference between partial, bounded, and trigger based. So based on that, EIGRP tends to have better performance compared to REB. But this comes with a cost, and the cost is the complicated implementation and maintenance. Because now I have to be very smart in detecting what the change is. I have to report only the change, and I have to report it to the routers that get affected by this change. Okay? Which is not an easy job. But if you do that, then the time to conversions will be faster. Why? Because I don't have to wait 30 seconds to report that there is a change. And I don't have to wait for repeated 30 seconds or repeated time interval until I propagate this change to the entire network. If I work trigger based, then if there is a change, I will report it immediately. And then the other router will realize that it's a change, so it will report it immediately. So the change will propagate in the network much faster. Right? If I talk about periodic updates, then every 30 seconds I report the entire routing table. So in order for any change to propagate throughout the network, you need minutes. You need many rounds until this change propagates to the entire network. But if you do trigger-based, then you reach faster. However, because of the partial updates and because of the bounded updates, the implementation for EIGRP is rather more complicated. Because to discover the change and to report only the change and to report it to the routers that get affected by the change, that's not an easy job. Okay? Anything that's not clear here, or okay? So that's the difference in terms of updates for EIGRP in comparison to REP, which is very straightforward. REP is very straightforward. It's just periodic updates. When there is any change, hopefully the change will get incorporated in the periodic routing updates, and it will reach when it reaches. So in terms of conversions, it's very slow. So the triggered updates talks about the fact that if there is any condition of change in the network, and this could be interface, one of the interfaces change its state. يعني one of the interfaces changes its state. يعني each interface represents a network or a local area network which is connected to this router port. For example, this one. Okay? So an interface changes state. This means that one of these interfaces, they go down. Okay? Which indicates that this network has become unreachable, unavailable. That's one example. Route becomes unreachable is because of the fact that this link is down. This router cannot reach to this LAN. Route is placed in the routing table. This is also a change. This triggers a change. If one router receives a triggered update, based on this triggered update, it inserts an entry in the routing table. So this is a triggered update in this router based on which it needs to send a triggered update. You see what I mean? So this all these three items, they are consequence of each other. So based on the interface change, this link becomes unreachable, in which case this router needs to send a triggered update that this link becomes down. Based on this triggered update, this router changes one of the entries in its routing table, whether delete or add. Okay? If the routing table changes, this means that this router needs to report this change. And when it reports this change only, which is partial updates. And it reports it only to the router that get affected by the change, which means that it will not send it back here. It sends it only to this router, because it knows that this router already knows about it. So it sends bounded update to this router. So that's how any change in the network propagates in a trigger-based fashion. Okay? Routing loops. You just have to concentrate very much here, because routing loops is a very important phenomenon that happens because of a inconsistent information in the routing tables of the routers. So this example here talks about the fact that these routers, they have reached a state of convergence, right? After the state of convergence, this link has gone down, which means that this entry in the routing table should be removed. And should here is an accurate word. Should be removed. Okay? So if this router removes this entry, which by the way, in the version, in RIP version 1 and version 2 and EIGRP, they don't do that directly. But let's just imagine that the router would remove this entry from the routing table. Remember that we are relying solely on the periodic updates here. Okay? So if this router removes this entry from the routing table, it waits for the next period in order for it to get the entire information in the routing table and send it to this router. Before doing that, this router will send message update to this router. Just imagine that this is the scenario that currently happens. Based on this router will receive the information from router 2. Remember, it does not have any entry for 10.4.0.0. It does not have any entry for that anymore because it removed it in this step. So you are receiving message update that tells you, by the way, I have a route to destination 10.4.0.0 with a hop count of 1. What would you do? So it will add this route to the table by mistake, and it will increment the metric to become 2. Assuming that if I send a packet to router 2 will be able to deliver this message to this destination. That's what it told me, right? It told me that I can get you to this destination with a hop count of 1. So based on that, if a message gets sent, if router 2 wants to send a message to a network which is 10.4.0.0, what will it do? Why? The routing table says that I can reach to 10.4.0.0 via this serial 001, which means that I have to send it to router 2. صح? Based on the routing table, that's what I have. When router 2 receives the message, what will it do? Based on the routing table, I have an entry for 10.4.0.0 to be sent to 001 to this router. So it will go in a loop forever. So this happens because I updated the routing table by mistake, and the routing tables have become inconsistent. So that's why we said that if there is a network change, we need to report that change very carefully. So this is a phenomena. A routing loop is a phenomena that we have to deal with very carefully. And there are multiple methods that allow me to deal with routing loops.
When the link was cancelled, shouldn't the routers update their table before starting to send the message?
The router removed the entry.
And shouldn't they send to the next router?
Because it does not do triggered updates. For RIP, it does not do triggered updates. And even assume that we send route update to this router. Just assume, okay? This route update will contain what? Will contain the information in the network, in the routing table, right? So this is the entry that will get received by router 2. Router 2 will go through it one by one. And it will figure out that there is no new information to the one that it already has. Because it does not have any information that this route has gone down. Based on the normal route update that we use, if I receive a message update from router 3, it will not contain any new information to the information that I already have. So, it has one entry which is missing, which indicates to me nothing because I'm better than you. I have more information. So we have to do something special to report the fact that this link has gone down. The normal procedure that we use in terms of periodic updates will not work in that case. Because this is a link that has gone down, which means that this entry will get removed. So this is a state of inconsistency, which we call it routing loop, and we need to deal with that. Okay? Any more questions?
This happens in RIP and
Yeah, this happens in all of them. Routing loops. This is one example or one scenario for routing loop. Routing loop is a phenomenon. Okay. Again, even RIP deals with routing loops. But in terms of the possibility that the routing loops will happen, they happen in all routing protocols. Why? Because as we said, even in the beginning, before reaching the state of conversions, routing tables are still inconsistent, right? So there is a possibility that routing loops might happen. Routing loops, as a phenomena, it happens in all routing protocols, and we need to deal with it. Now, RIP uses some certain methods. EIGRP deals with it naturally using the triggered updates and so on and so forth. But RIP needs to do something very special. So we need to go out of the normal procedure of periodic updates, and each message update will contain the routing table. So we need to go away from this. We need to think differently. There are special methods that we have to put in place for RIP to deal with the routing protocol or routing loops. Okay? So we'll talk about that next time.